This is the second video lecture on rational functions. Here I'll go through several examples of rational functions. Okay, in this case what I'm going to do is go through the steps that you should go through in plotting and understanding the rational function. Generally you need a computer to really plot a rational function, but you have to determine these things, and that's what's required in this class. So detailed calculations, detailed plots of rational functions are not required. Alright, so we're given a rational function here. Let's just say it's 4 over x squared minus 9. First thing you need to do is find the vertical asymptotes. To find the vertical asymptote, take the denominator and set it equal to 0 and find those values of x. So x squared minus 9 equals 0. Obviously there's two roots of this equation, x equals 3 and minus 3. So when you go to the graph on your graphing paper, draw a vertical dashed line at 3 and minus 3. I'd like to say a note about graphing calculators. Sometimes you'll see a line through the vertical asymptote. This is actually, it looks like a vertical line, but it really isn't. Sometimes the graphing calculators make mistakes, and they can't plot, of course, at x equals 3, but if you have a point on either side of it, it will connect those points, and because it can look like a vertical line, it's actually a mistake. Alright, so now you found the vertical asymptotes and you drew vertical dashed lines on the graph. Now find the horizontal asymptote. To find that, look at the degree of the numerator. In this case it's just a 4, so its degree is 0. And look at the degree of the denominator, and that's of degree 2, and compare them. Since the degree of the numerator is greater than the degree of the denominator, the horizontal asymptote is y equals 0. So you can draw a horizontal dashed line on the graph for y equals 0, which is, of course, is just on the x-axis. Now the next thing to determine in the rational function are the X axis intercepts. That is, where does this function cross the axis? To find that out, set the numerator equal to 0. Well, there's no solution for that, because you have 4 equal to 0, of course no solution, so it never crosses the x-axis. So here's a graph of this function. You see a vertical asymptote at x equal minus 3. Here's another one at x equals plus 3. And the horizontal asymptote is at y equals 0. Now to sketch the function in between, you need several points. You can use some reasoning and figure that it never crosses the x-axis, which actually it doesn't cross, it just looks close to here. It looks very close to the x-axis, but it doesn't cross it. It's just a scale. In order to show the behavior of the function, I can't show the detail right at near the x-axis line. Now here's the same function with a little change. Instead of 4 over x squared minus 9, I now have 4x over x squared minus 9. So that's a different numerator. So again, to find the vertical asymptote, set the denominator equal to 0. We already did this, but I wrote it here anyway. So you set the x squared minus 9, you take the denominator, you set it equal to 0, and you solve. In this case, of course, as before, you have two roots, 3 and minus 3. Those are your vertical asymptotes. They appear as vertical dashed lines on the graph. Now find the horizontal asymptote. To do that, you compare the degree of the numerator. In this case, this is numerator is of degree 1. The denominator is of degree 2. Since the degree of the numerator is greater than the degree of the denominator, then y equals 0 is your horizontal asymptote. So this function in the long run approaches the x-axis. And now you want to find the X Axis Intercepts. To do that, set the numerator to 0. Well, the numerator is 4x, so x equals 0 is the solution of that. This means that the graph crosses the x-axis at x equals 0. If there's a multiplicity in the root, it may not cross. It might just touch the x-axis and turn around. But in this case, it does cross it. So here's a graph of this function, 4x divided by x squared minus 9. Here's the vertical asymptote at x equal minus 3. Here's another vertical asymptote at x equal 3. As the function approaches the vertical asymptote, it either goes to plus infinity or minus infinity on either side. So we've seen the same behavior over and over again. And to find out which one it does, you have to start plotting some points. Okay. Now in this case, we have an x-axis crossing, and I marked it here with a star. So there's the x-axis intercept. And this function, you see it's positive here for these values of x, and then it becomes negative because it crosses the x-axis. Those x-axis crossings are the only places that the function will cross the x-axis. They're the only places. And they're found by setting the numerator equal to 0. For the horizontal asymptote, we found that was y equals 0. There's a horizontal asymptote, and you can see the function approaching the x-axis, approaching the line y equals 0 as x becomes larger, or very, very positive, or very, very negative. So here's a third example, and we're going to go through exactly the same routine. We're going to find the vertical asymptotes. To do that, you take the denominator and you set it equal to 0. You solve again. In this case, it's plus 3 and minus 3. Those are your vertical asymptotes. They are shown as vertical dashed lines on the graph. I mean, you don't have to show them, but they aren't really part of the graph, but it helps to sketch them in. It kind of makes a little framework for drawing the rest of the graph. Now we look for the horizontal asymptote. To find the horizontal asymptote, you compare the degree of the numerator, and this was degree 2. Compare it to the degree of the denominator. This is of degree 2. They are equal. Since they're equal, the vertical asymptote is the fraction made out of the leading coefficient. The leading coefficient here is 40. The leading coefficient here, of course, is 1. Make a fraction out of that, which of course is just y equal 40. Then you can draw a horizontal dashed line on the graph for y equal 40, and that is your horizontal asymptote. That is the value that the function will level off to in the long run. Now let's look for x-axis intercepts. So you take the numerator, that'll be this whole thing here, and you set it equal to 0 and solve. Okay, two solutions here, 10 and minus 10. Those are the two places and the only two places where this graph crosses the x-axis. So here's a graph of this function. You see vertical asymptotes again at plus 3 and minus 3. The x-axis crossings were at minus 10 and plus 10. You see the function cross the x-axis there? Okay, that's the only place it crosses or touches the x-axis. I put little stars there. Now for the horizontal asymptote, because the degree of the numerator was 2 and the degree of the polynomial was the denominator was 2, that means they have the same degree. The horizontal asymptote is a fraction made out of the leading coefficients, in this case 40 over 1. So here's your y equal 40, and it is a horizontal asymptote. Here's the problem from the homework. So we have a rational function. Numerator is 2x to the 4th minus 32. The denominator is x to the 4th minus 36x squared. So we do the same thing again. First we have to find the vertical asymptotes. To do that, take your denominator, which is x to the 4th minus 32x squared, and set it equal to 0 and solve it. Here I had to do some factoring, and I came up with 3 roots. Well, actually 4. There are 4 roots because x equals 0 has a multiplicity of 2. So here are the 3 vertical asymptotes. X equals 0, x equals 6, and x equals minus 6. Those appear on the graph as a vertical, dashed vertical line if you choose to draw them in. Okay. Now let's determine the horizontal asymptote. To do that, we look at the degree of the numerator, and this is of degree 4, and we look at the degree of the denominator. It is 4, right? So they're equal. Since they're equal, the horizontal asymptote is a fraction made out of the leading coefficients. So the leading coefficient here is a 2, and here, of course, it's a 1. So this is my horizontal asymptote. It's y equal 2. That is the value that the function will level off to as x approaches either negative infinity or as it's approaching positive infinity. Now we want to find out where it crosses the x-axis. To do that, you take the numerator. Well, that should have been up. Sorry. Okay. Take this numerator and set it equal to 0 and solve it. Okay, x to the 4th equals 16. The solution is x equal 2 or x equal minus 2. Those are the places where the function will cross the x-axis, and those are the only places where the function will either touch or cross the x-axis. Now for the homework, you have to plot a couple extra points and then try to use some reasoning and connect up what's going on. All right, but here we have it sketched out. Whoops, sorry. We have a vertical asymptote at 6, a vertical asymptote at minus 6, and another vertical asymptote at along x equals 0. You see how the function approaches either plus infinity or minus infinity as it goes close to the vertical asymptote. Then we have these two dots here at plus 2 and minus 2. Those are the two places where the function will cross the x-axis. So in other words, if the function is positive here, it has to stay positive, and that's one way you can figure out if it's going to go to plus infinity. For example, if you look at it at this point right here and you find it's positive, as it approaches x equals 0, it can't turn around and do this because that means it would have to cross the x-axis, which it doesn't do. So it will stay positive, and you can kind of use some reasoning to figure out how the function is going to look. It doesn't have to be a detailed plot. Just plot up some points and use some reasoning. Okay, and now, of course, the horizontal asymptote is y equal 2. And this is a good example here. Let me erase the screen a minute. It's a good example showing that the function crosses the horizontal asymptote. See how it crosses x equal 2 in these places? And that's okay because that's far away from the long-term behavior. The long-term behavior settles down to y equals 2.